Hello and welcome to EngFiz2P04's Essential FlexPDE.docx overview. We're going to be going over how to use FlexPDE. This is a file that's been on the website for a while, but this is going to be a video overview of this to talk you through this. Okay, so this is a standalone thing. If you found your way to this video and haven't done any of the other ones, no problem. All you need is to get FlexPDE version 6 student installed, and I'll put a link in the description for where you can go to get that. Okay, so FlexPDE is a finite element method solver that can solve partial differential equations on 2 or 3 dimensional grids. It can also do this on 1 dimensional grids. It can do ordinary differential equations, and it does this by using the finite element method in space and I believe something like the finite difference method in time. What this means is it's doing numeric solutions. So if none of that makes much sense to you, then for now it's doing numeric solutions to find best guesses at solutions to differential equations. So let's just load it up and get started here. I'm going to click on the FlexPDE icon, and when you load up the student version, you'll see something like this. Then you can create a new file, File New, or Control N for that. Now, actually, I should say, before we even go further, if you've loaded up Flex and it looks all blurry, which it will do by default in Windows 10, then there's a trick to fixing that I'll show you now. So open the Start menu and start typing FlexPDE 6S, and then open the file location of this. This tells you where the shortcut is for your Start menu, and then in here you can go to Properties and find out where the actual FlexPDE file is. If you'd like to change it for any time you load it, or you can just do this in the compatibility menu here. It's under high DPI settings and override high DPI scaling behavior performed by application. This you might not need to do if you don't have much resolution on your monitor. So when using a laptop, it might not have mattered. But if you have like a 4K display, then this is definitely necessary. It's going to be very blurry otherwise. It might even be necessary even if you don't have a lot of resolution, depending on your computer. Okay, so you can either do this in the shortcut, or you can copy the location here, find out where it's actually located, open up a new Explorer window, which is window key E, paste in that path, and you can go right to there, or you can just navigate to C drive FlexPDE 6 student, and then go to the actual FlexPDE 6S file. You can see this is what's being referred to by the shortcut. So in this thing, we can right click, go to Properties, and we have the same kind of compatibility stuff as before, where we can override the high DPI scaling behavior performed by the application. Yeah, so you'll need to do this with older coded applications like FlexPDE and probably with Maple, depending on what version of Maple you're running. Okay, so now that that's done, we can create a new file with Control N, and it always seems to start in the installation directory here, this FlexPDE 6 student. I'm going to go to the 2P04 directory first week topic that we're working on now, and then go into Essential FlexPDE, this folder that I made ahead of time for that. If you don't have folders made, you can actually just make them from within this menu too. You don't have to pre-make them. Anyway, in here, I'm going to make the name of my new .pde file. .pde is the extension for a FlexPDE file. So this is the code that that FlexPDE is going to run. So let's go Essential 1. Sure, let's call it that. Okay, so now we've got this file, and we're looking at it from within FlexPDE. If we open up the Explorer window for this directory, then you can see that we have now created a .pde file and a .dbg file. So you can look at what these contain by opening them up in Notepad, maybe Notepad++. And the PDE file looks like it has exactly the same stuff as it does in FlexPDE, but not as colored. So this is just stored as a regular text file. And we can have a look at the other file as well. The .dbg file seems like it's empty right now. Okay, so let's keep an eye on that. Maybe it'll do something different after we run the code. Let's see. To actually run the code here, what you do is you hit the lightning bolt, or just hit Control R, and maybe you can see there's a pop-up thing that shows up here when you're hovering over the lightning bolt that tells you what the shortcut key is. I just hit Windows Shift S here to take a screenshot, by the way, which is going to be pretty useful for making quick free body diagrams or clips of results and putting them in your Word files or your word processor files later. Okay, anyway, run, Control R, here we go. Control R, it flickers a little bit. It might take a little longer for you depending on the computer you're using. And this actually has gone and solved this differential equation. Control E to go back to the code, Control R to run again and go to the results. So back to the code, Control E. It runs this equation, div of the grad of u is equal to 0, solving this on a grid, which is a square grid from 0, 0 to 1, 1, which is oriented with the XY plane. So conveniently with Notepad++, whenever the file changes, we get some notification. So here the essential database file has been updated and we can reload it. And now we see some information in here which is telling us about the results of running this simulation. Because the simulation is not very intense, this file is not very long, but for a long, complicated process of doing finite element method, you might expect, you might find that this DBG file is quite long indeed. Okay, now if we go back to the notes, it tells us that this creates a .pg6 file by running it. So we can look in the folder, and indeed, there's a couple of things. There's a log file, which is sort of a brief summary of what happened in running this thing. There is a pg6 file, which also has an icon, and the icon looks very similar to the .pde file, so people often mistake it. Don't fall for the trap. This is the one that's the code and says what you're, and carries the information to run the script that you ran. This one, let's have a look. This file is nonsense. This is something that's used internally by FlexPDE. It actually stores, in some cases, the results of the script. So you remember this is one of the things that this is sort of the result window, right? It looks like this, but that's not what you want in showing somebody else how you got that result. You probably want the code, which has all the information of the mesh, the results of running it, and where it came from. This pg6 file doesn't contain any of that. It just contains it's just the holding place for the results of running this code. So if you are going to be sharing your code with somebody else, share the .pde file, not the pg6 file. All right, so again, we've solved div of grad u is equal to 0. You can see the equation we're solving under the equations part in FlexPDE. Anything, by the way, that's green here is a comment. There's two different ways to comment, which one way is with the curly braces here. This starts and then ends a comment with the open and close of it. If we put another open one here, it'll comment out the whole rest of the program because this one isn't paired with anything. Another way to start a comment is with this exclamation mark. So this will just comment out the whole rest of the line. When you start a new file, the default file has a bunch of these commenting marks over things you maybe don't need to have in there. So this will still run just by saying what the variable is, what the equation is we're going to solve, and what boundary region we are going to solve it on without needing any monitors specified. So this isn't doing anything right now. And we've only got one plot at the end. We want to make a contour plot of u, and that's just showing us a contour plot. It's not very interesting because the differential equation that we're solving is that the Laplacian of u is equal to 0, and that since we didn't specify a boundary condition, so under boundaries, we just drew the shape but didn't say any values or loads on u. The default one turns out to be that the partial derivative of the thing we're solving of u in the direction perpendicular to the boundary is equal to 0. So the directional derivative of u outwards on this, so the outward gradient of u is equal to 0. So there's no flux of u leaving this region. And that ends up being pretty boring of a solution. One way that we can make it more interesting is by specifying some different values somewhere. So let's suppose on this, this last part, first of all, maybe before we talk about the boundary, the values we can specify, let's talk about the shape. This is starting at 0, 0, and then taking a line to 1, 0, and then to 1, 1, and then to 0, 1, and then to close. So what that does is it starts here. This is kind of drawing the mesh. It says we're going to solve whatever we're solving, starting from 0, 0, and then take a line over to 1, 0, and then up to 1, 1, and then over to 0, 1, and then back down to close, which since we started at 0, 0 means right here. Yeah, so that is the shape. That's why we get a square here. Let's modify that. Let's go maybe line to 2, 1. Think about what this might do. We're going to go 0, 0, and then we're going to go over to 1, 0. Then we're going to go up to 2, 1. Wait, 2, 1 is further over to the right and still 1 up. And then over to 0, 1, and then down to close. So this should make something which looks like a sand dune. Yeah, okay, so this one of these shapes, which I guess is a trapezoid. Yeah, trapezoid. Okay, so we've got a trapezoidal region now. Still very boring because we didn't specify any different boundary conditions, but let's set some. So how do we do that? Well, first we can go and insert the rest of these line commands. So this before the 2 doesn't do anything. It's kind of implied. If you have a bunch of different points and you're going to have a line to each of them, then you don't have to write the line command before each 2, and it will carry it all the way through. So this is exactly the same, but written like this, we can more easily specify a boundary condition change. So start at 0, 0, no change to the boundary condition, line to 1, 0. The default boundary condition is that load of u is equal to 0. So now we're just kind of sticking with that. But let's put in something different after the next one. So maybe before we do this line to 2, 1, we'll say value of u is equal to 10. And then before we do the line to close, which is this left line, we'll go value of u is equal to 5. Okay, so now we expect something different. We need a value of 10 on the right-hand side and a value of 5 on the left-hand side and no outward flux on the top or bottom. All right. Yeah, so physically, Laplace's equation turns out to be what you would get for a steady-state heat distribution. And one thing I forgot to mention is since we didn't re-specify anything here, it doesn't go back to load u is equal to 0. It sticks with value of u is equal to 10, the last one we set. So first, let's go back to this. And now it's a little bit more like you might have expected. So this is fixed to 10 degrees over here, fixed to 5 degrees over here, and insulating on the side. So no heat can escape the top and bottom. If you wait long enough, what's the temperature going to look like? That's what this equation happens to be solving. This is Laplace's equation. We'll look at this a lot more in a heat transfer course. So for EngPhys people watching this, you'll learn about it in computational multiphysics at the beginning, and then more in EngPhys 3004. Okay, so we can make this plot look a little bit nicer by going painted, and that will fill it in, and that's kind of cool. What about when we didn't have this load of u is equal to 0 thing there? So we can delete it, or you could just comment it out. Now it's going to keep this value of u is equal to 10 all along that top surface. So there we go. We've got 10 here and 10 there. The colors, the auto scaling of the color bar changed, but it still is equal to 10 at the top and the side, just like it was before we did that. See red now, but 10, so the scale changed. Don't be fooled by a changing scale. The notes walk you through the same information with a different example, so check those out too and give that a shot. One thing I haven't mentioned yet is that FlexPDE is case and line break insensitive. You may have noticed that nothing changed when I added in these line breaks and wrote it out by putting something on the next line. If we run it like this, there's no difference. You can put in a line break anywhere you like in here, no problem. Potentially anywhere you like, maybe not here. Let's see. Nope, doesn't even care. Okay, so it's totally line break insensitive. It's also case insensitive. You can call this region and it doesn't get upset. You can change the keyword to something like that. Whoop. If you still spell it right, you got to spell it right. That's the advantage of having this color coding. So something, I should have known something was wrong when it didn't turn red until after I put in that A in there. Okay, so as you can see, it doesn't care about the case of the letters. So small b is the same as big B. That's what case insensitive means. But that doesn't mean that you should be ridiculous like this, unless of course you really want to. Another thing that you can do, which you might enjoy, is changing the font. So some people in previous years, as soon as they found out about this, decided, all right, everything is in Comic Sans. In FlexPDE, you can totally code like this if you really feel like it. I recommend that you use a mono-spaced font whenever you're coding to make it, or at least something that's reasonably mono-spaced to make it easy to tell where you, where the white space characters are and where things are supposed to be, how they line up, that sort of thing. All right, next up, we're going to go over how to have time derivatives instead of space derivatives. This is a little bit overkill to use FlexPDE as a solver for time derivatives, but it's actually pretty convenient for that, and we're going to need it for those space derivative things later on in the course. At the beginning of the course, we're going to do time derivative stuff. So what that means is instead of solving this like spatial dependence differential equation, where we're taking derivatives of u with respect to x and y by using div of grad here, what we're going to do is take dt of u is equal to 0. Now, to make this work, we need to specify some other things. So for time changing variables, you need a threshold. This tells Flex how much of a fractional change in u we should care about. It's a measure of precision. If you put this to a lower number, then it's going to get more precise. You put it to a higher number, it's going to be less precise, but then run faster. So a trade-off there. Okay, what else? We need to put in an initial value now. So because it's time dependent, we need the initial value section. Maybe just u is equal to 0 is the default one, but then that won't be very interesting. U is equal to 1. And we can specify how much time we want this to run for. So time 0 to 1, we'll need that. And then at the end, we'll put a range of time that we want to plot it for t equals 0 by 0.1 to end time. This actually means that we're going to have a series of plots. So it's not just going to plot the final value, it's going to make a plot for all different times. Let's not actually change everything else and just see what happens here. So what this did is it made the contour plot starting at time 0 and ran in steps of 0.1 to end time. So you'll see it flash a bunch of times. It's actually solving a number of different things. If we change this to, let's say 100, and just to make it not take forever, actually I wonder, how long is this going to take? Let's go to 10 first. Okay, so this is kind of a lot, and it's really flickery. It's hard to watch. Yeah, so that's way too long. What you can do is you can say by end time over 10, if you just want 10 plots, 10 different steps, no matter what, or go like 100 of them here. That's so this is taking time to 100, but still 10 different steps because of how we set this up. Now this is sort of inconvenient, right? Like this, oh, by the way, this is another way to go right to the results. You don't have to rerun it every time. It's Control L, but because that requires moving your hand off of the mouse, for me, I usually just like rerun it again and use simulations that run kind of fast. But if you want to go right to the end, you can click on this instead of hitting Control L. Okay. Rather than plotting the whole contour, what you can do is look at just one spot. And that's something you can do with a history plot. History u at location 0, 0. So this is going to plot versus time what u is at that spot. Now, because we specified that u has to be equal to 5 at this edge, the history plot, by the way, after you've double-clicked on the mesh to make it full screen, double-click on it again to put it back. The history plot is just staying at 5 for all time. We can modify this by either looking somewhere different, maybe in the middle. It doesn't change much there. It's sort of set near the initial value of u equals 1 over this time scale. Let's go 1,000, 100,000, sort of staying forever. Actually, it's not quite at the value of 1. Maybe we're looking too coarse in time. You know what? We said that no change in time. So that's why nothing's changing. Let's change this to 5. Now we can see some modifications happening as we step forward in time. We could set this to 1 and see a lot more change happening. 10, 1,000. So it's always increasing in time at this center point. This is like a heating up forever. If u represents heat, that is. The rate of change of u is equal to 5, and it just increases. The rate of change of u is equal to 5. It increases forever as we run things in time here. Okay, let's get rid of these funky boundary conditions and just stick with the default of load of u is equal to 0. So the edges are not messing with anything. Okay, now we can run it to 1. And let's look at what we're actually solving here. We're solving an initial value of 1. The slope of u is equal to 5. And run time forward. So if we start at 1 and we've got a slope everywhere of 5, nothing changes in space. So you actually can ignore the spatial dependence of this thing and just kind of forget about the fact that it even has a grid, and look at what u is as we go from 0 to time 1. So if we start at 1 and we have a slope of 5 all the time, and we move 1 unit of time into the future, we should end up at 1 plus 5 is 6. Okay, great. What if we went 2 units of time into the future? We should end up at 1 plus 2 times 5 should be 11. So how can we do that? We can change the end time here to 2. And now we'll go up to, sure enough, 11. Okay, so this is solving the differential equation that the slope of u in time, the rate of change of u, is equal to 5. When we start at an initial value of 1 for the time from 0 to 2. But that one is a pretty easy differential equation. Can we solve a more complicated one? What about the slope of u is -3 plus 2 times u on the range 0 to 1? Try this out for yourself. Okay, let's give it a shot. We're going to go time 0 to 1. And now the equation that we're solving is -3 plus 2 times u. We don't need any spatial dependence, so we can leave all this boundary stuff alone. And we're going 0 to 1, yep. Sure, this really just affects how precisely you look at it in plotting. And it'll be the same everywhere on the grid, so it doesn't matter that it's 0.5, 0.5. All right, so let's think about it for a second. This looks like this picture, and that probably means it's right. But I really want to emphasize that you need to do this second step of the physics afterwards. Whenever you're solving something, now this is maybe just math, not even physics yet, but it's extra essential in physics. After you get the answer, don't just say, yeah, that looks good. Think about what this means. So why does it go like this? Why does it start off with this negative slope here and then start to decrease at increasingly more negative slopes? Well, it starts at a value of 1 because we had an initial value of 1 still. That the problem actually didn't tell us what the initial value was. It should have, so we just stuck with the previous one, and that's okay. All right. Now, why does it have a negative slope at the start? Well, the slope is supposed to be -3 minus or plus 2 times whatever u is. And if u is 1, That means we get a slope of -1 at the start. And because we have a slope of -1, we're decreasing as we move forward in time. And as u gets more gets lower, because we had a negative slope, u gets smaller after a little bit of time. Like around here, it looks like it's about 0.75. Now, that with u being smaller, we're not adding 2 times 1, we're adding 2 times 0.75. That's only 1.5. So we end up with a more negative slope. Instead of -3 plus 2, we've got -3 plus 1.5, or -1.5. And this continues. This differential equation, now maybe, I don't know about you, but just even talking it through like that, I've got a much better feeling for how this works. You've got to think it through every time, right? Like this thing you can see as u goes forward, because we have this negative slope initially, we're going to be getting more and more negative. So that's why it's kind of folding down like this. But another thing you might have thought about is, hey, you know, if we start at a certain value of u here, if 2 times u happens to be the same as +3, this should just hold still the whole time. Okay, so let's change the initial value to 1.5. That'll make that happen. Yeah, no motion. There's this green line just holding still there. What if 2 times u is bigger than 3? Well, then we're going to be, with a positive slope, increasing what u is, which is going to increase the slope more, so it's going to increase more and more and more. Okay, so let's try 2. Yeah, so you might say in solving differential equations that u is equal to 1.5 is a possible steady state solution for this thing, but it's an unstable equilibrium, because if it goes a little bit up from there or a little bit down, this differential equation is going to cause it to go further away in time. All right, some tricks. Rather than plotting this, we often want to know what the value is at a certain time, like when we've stopped the solution here. So we could read this off the plot like we've been doing here, and say, well, it looks like it's kind of 4.5 to 5, and 1, 2, 3, 4, 5 divisions. So each division is 0.1, and that means we're at about 5.2 there. But rather than having to do that every time, you could just put in a report. So this is with a new section here called Summary, and the syntax is, in this case, report eval u00 as final value of u. Okay, here we go. Final value of u is 5.2, and that's about what we thought there. Let's explore this a bit. What if we don't say this? It'll just say the code. Eval u00 is that. What's the 00 about? Those are coordinates. So that has to be coordinates within the region that we drew there. If we said eval 50, does it care? No, actually, it turns out it doesn't care in this situation, but we're reporting something outside the grid. So if we were solving a space-dependent thing, this might be giving us trouble. What next? Report val of u at 00 also works. There's some subtle differences between report value and report eval that show up in some situations. But in this case, they end up being the same thing. So you could use either one of those. You can rename it if you like, rather than just using the code. Up to you. Okay, you can also just report the time. And this is kind of useful because it reminds you what value of the time we're stopping at. I mean, if you don't do that, then you still have that written at the bottom. So again, kind of optional for what you report there. But this is nice in that we don't have to read off the plot for that value if we use something like this summary section. All right, let's suppose we wanted a much more detailed thing. So we're going to make the end time 10, and we're going to take, let's say, 1,000 points on the way there. So now this takes a while to run. It's got this exponential growth, so it's going to take a while to finish. It might take quite a lot longer depending on what kind of computer you're running. This is a while, right? Like it's a very large number at the end. We're close to because of how exponential growth works, we wouldn't have to let this go too much further before we're into truly obscene numbers. And this took what? We can see how long it took to solve. Yeah, right at the top, 7 seconds to solve that. Let's see if we can optimize. One way is by changing this grid density. Since we're not actually using all of these grid points anyway, because there's no spatial dependence for this problem, we can change that in the select section. This is method controls, like the way that it's solving controls. And one that you're going to set until we have spatial dependence is ngrid is equal to 1. This tells you about the grid density. And now we solve the same problem. Instead of 7 seconds, it solves it in 5 seconds. Okay, so not too much in this particular case, because we're mostly limited by how fast it can refresh the screen in this one, because we called for a lot of plots. But it's that is going to be saving time that matters in a lot of examples. It'll be more like a factor of 10 savings of time rather than this like small 2-second time difference. So set ngrid is equal to 1 if you don't care about the spatial dependence of your problem like this one. Another thing you can do is set up definitions. So in the code, it's bad practice for us to have magic numbers like this usually in the differential equation, unless there's something fundamental about why this 3 is there. So we could change that by using the definition section. Let's imagine we want to say like m is 7, g is 9.81, and then we'll say dt of u is negative m times g. So this is a different differential equation, but now it's meaningful for what's going on here, at least if we were to comment in here and say something like mass maybe, and gravitational acceleration. Since it's 9.81, you probably would recognize that without the comment, but anyway, you can put in these things to clarify what your variables are if you want to be more clear. Okay, so now we just have this gravity acceleration with 1,000 points in the plot. It's taking about as long even without this exponential growth because of all the refreshing we're asking it to do on this screen. Okay, yeah, another thing we can do is plot more than one thing at once. So we could have, let's say, one variable and then another variable and plot them both while we're solving this thing. This is only going to be valid if we have more than one variable that we'd like to plot. So for now, what we can do is plot, let's say, u and maybe u squared. Sure. Now we've got colors, plotting more than one thing at once, u and u squared. Beautiful. Okay, let's go on to a more difficult problem. This is a second-order differential equation. The second derivative of u with respect to time is negative 9.81. Let's see. How might we solve this? You might be tempted to say dt of u is equal to negative, so the acceleration, maybe mass times this thing, is equal to, or maybe acceleration. Yeah, there we go. The second derivative of u is equal to negative g. This is just gravitational acceleration. Oh, but it's illegal. We can't have a second derivative of u in here. So one way to solve it is to set up a whole other variable. Let's say v. Threshold is 0.1. And this will be like the velocity, let's say. And now we can say the initial value is equal to 0. That's the default. If we don't say that, it's the same as having it there. And this is a nice trick. Now we need to specify what equation corresponds to each variable. But we can say the derivative of u is equal to the velocity. And for v, we'll say that its derivative is equal to the acceleration. Okay, so this way, it's like we've created a middleman so that the derivative of v, which would be the second derivative of u by this definition, is equal to negative g. But now we can solve it. right? It didn't complain. We haven't actually told it to report the outcome yet. So we'll do that. End time over, let's say 10. History of U, and let's go with V at this point. And then report value of U there, and V, final value of V. Remember to change the, oh, I guess this is in the comment. This doesn't matter. It's just showing us the values here. Okay, so there we go. Here's our U. Parabolic motion for this in time. When something's just starting at a velocity of 0 and accelerating in time from gravity, and then this downward velocity there. So this velocity that's getting more and more negative as we move through time. So this is something to keep in mind. If you start something at a position of 2 meters, and then you let it accelerate with respect to gravity, so just from gravitational acceleration, for 10 seconds, how far down is it? Well, according to this, it's almost 500 meters down. Wow. Does that make sense? Let's think about it. The velocity, 10 seconds later, if we've got an acceleration of about 10 meters per second, will be 100 meters per second, right? So initially it's going 0 meters per second. 10 seconds later, it's going at 100 meters per second down. That's the negative here. And we've got that for the velocity. All right, so what was the average? It's linearly changing from 0 to negative 100. So the average is negative 50. And negative 50 times 10 seconds is going to get you to 500 meters down. So, okay, that's the kind of sense check that you want to do at the end of this to say, all right, yeah, it looks like we are in the right range here. It doesn't take too long to do those physics sense checks afterwards, and it increases your understanding of this kind of a problem so much. So please do it. Think about how this thing works, what kind of shape you expected here, how it what it was about the differential equation that led to this, and then anticipate how things should work differently. So what if you change this to 50? Now what do you expect? Well, it means that it's starting off going at 50 meters per second up. And since negative 50 was the average last time, we should end up close to where we started, if not exactly where we started. Let's see. Value of U is pretty close. So you see there's some round off error here. Actually, the round off error is me, right? Because it wasn't exactly, G isn't exactly 10. Let's make G exactly 10 and see how that looks. Aha. So now we're at exactly 2 because, right, I'll think, maybe you already understand what I'm going for here. The average was not quite negative 50 because it was only negative 50 if we're assuming G is exactly 10. So when we made V start at 50, now we move from a velocity of plus 50 to a velocity of exactly negative 50 after 10 seconds, meaning the average velocity is exactly 0. So over this amount of time, 10 seconds exactly, we end up at the same spot that we started. So this is good because it shows us what the precision of FlexPDE is for this. We found some definite numeric precision limiting stuff, and we can try to change around some of the things at the start to see what makes a difference here. So imagine we change the threshold on these variables. Does that make a difference? No, that doesn't affect this. What about the time step that we're solving it at? Time is 0 to 10 by 1e minus 3. No change. 1e minus 5. Aha! So telling it to solve with more steps does seem to make a difference in how accurate we're getting here at the end. Okay, and that concludes what we wanted to talk about today with FlexPDE. You now have all the information needed to solve arbitrary first and second order PDEs in Flex. Such power.